I tell you something. In the last O-level classes, when I was conducting O-level marathons, A-level students hopped in the class and said, "Sir, please do A-level, please do A-level." Now in the A-level marathon, O-levels are hopping in. That's the thing about all of us. We are never happy with whatever we've got, and we also are very selfish as human beings. We couldn't care less. A-level students don't care about O-level students right now, and O-level students don't care about A-level students right now. They just want the teacher to just magically wave their wands and teach you entire chemistry in one day. But sorry to bust your bubble, that's not possible in a single day, is it? Just let me go with my pace. I'll cover things with A-level students as well. Like I've promised, over the weekend I'll conduct one marathon class for organic chemistry in which I'll cover all the mechanisms and every single reaction in a lot of detail. It'll be a 4 to 5 hour class, and then I'll also talk about organic synthesis. And then my liability towards the A-level students will be discharged. Yes, I'll also try to do other summary classes or marathon classes for other chapters, which I've not yet covered in marathons. I've covered every single chapter in a lot of detail, but students who are waiting on the marathons, who don't want to study the detailed classes, they can get that later on if I get the time. It's not a promise. Again, I'm not committing to anything. Don't hold me to that, but I'll try my level best to do something for those students who wake up during the last hours. So it's a horse race. What do you expect? No, Mariam, it's not a horse race. Please don't call yourself horses. It's a rat race. This is what we've, reduced ourselves to, unfortunately, as students. We couldn't care less. We don't even tell to other friends about, good teachers in the market. You know why? Because we are selfish. We think that, oh my God, if I tell Flana, if I tell Bushra Bhane, oh my God, she's gonna get a good grade, and then, oh my God, the threshold's gonna get high. That's how our thought process is. It's all negative, 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 unfortunately. So that's something we need to work on. And so without further ado, I think I should just start solving the alkene questions, because I've given you guys dose. Sir, I did your advertisement. This is not the time to do my advertisement, Raima. You should have done the advertisement when you were taking the classes and enjoying them and acing every single chapter because of the detailed classes and gatekeeping me. It's not the time to advertise me. I think it's better to not advertise me right now because your friends are gonna curse you all, for gatekeeping me. I think I brought all my homies to the class. That's awesome. That's awesome. That's good. As long as you do your part in helping others out. I'm not saying, tell everybody about me. The reason why I do that is because I know that A levels is a piece of cake, and teachers tend to make it so difficult for students that they get students bamboozled. So it's very, very important to select the right teachers for A levels, especially A levels. A levels is easier than O levels, and I've proven that through my live classes. Those who have consistently taken my live classes, because obviously my course is pretty lengthy. It's 134-hour course, or 134 lectures in totality. Even now, if somebody were to take them to just cover organic chemistry or some other parts of chemistry which are weak, they can absolutely do that. Okay, without further ado, let's just start solving the questions from my topical booklet. Chapter 13, Alkenes and Polymerization. Question number 1. Cobalt, rhodium and iridium are metals in the same group of the periodic table. Okay, good going. Next. Hydrated rhodium 3 chloride catalyzes. This 3 basically represents the oxidation number of rhodium, by the way. It says it catalyzes the conversion of ethane to butene. Is this part of your course? No. Do I need to know that this fella catalyzes the conversion of ethane to butene? No. He's just giving me information, and I'll just abide by it. I'll go, okay, if you are saying it does it, I'll say it does it. Now it says both stereoisomers of butene are formed in the reaction. Hold right here. Butene, you know that there are two types of stereoisomers. One is optical isomerism and the other one is geometric isomerism. Optical isomerism exists if a carbon is a chiral carbon, that is in fact a chiral center. And what do we mean by a chiral carbon or a chiral center? A chiral carbon or a chiral center just means that the carbon must be bonded to 4 different groups or 4 different atoms, right? So that's one case. That's what we call optical isomers. And when we talk about the other type of stereoisomerism, which is geometric geometric isomers, which is normally exhibited by these double bond alkenes, is that the carbon in the double bond, both the carbons in the double bond, each of the carbon in the double bond must be bonded to two different atoms or two different groups, right? So if this is A and this should be B, then if this is A, this should be B then, right? Or if this is C, this should be D. They both can't be the same. They both can't be A. If they're both A or if they're both B, if they're both the same atoms or the same groups, it can't exhibit geometric isomerism, which we also call cis-trans isomerism, right? You need to have two different groups or two different atoms bonded to each of the carbon in the double bond, and that's how you exhibit cis and trans isomerism. How do I know which one is cis and which one is trans? Remember, if both the carbons in the double bond are present, and if you look at the atoms or the groups bonded to each of the carbon, if these both groups are on the same side, we say on the same side, see, both the A atoms are on the same side, they're both on the same side, we call them Z isomers or cis isomers. Cis or Z, if you're a PSN and Excel student, they also use the EZ notation. So it's cis, the same side is cis. But what if they are on the opposite sides? Then, like for example, A is here and then A is here, and B was bonded to this carbon and then B is bonded to this carbon. If the atoms, if these groups, the same groups, if they are on the opposite sides, then we call them trans isomers, or even as E notation. In the EZ notation, we call them the E isomer, right? That's the idea. Now, moving on. So if you have but2ene, and the way you draw the skeletal for it, remember the cis isomer, when we draw the skeletal for the cis isomer, we draw it like an inverted boat, right? Like an inverted boat. Why? You see, if this is but2ene, but means 4 carbons, 1, 2, 3, 4, and 2e means that the carbon-carbon double bond is between the second and the third carbon. And to check this fella out, you have 1 carbon, 2 carbon, 3 carbon, 4 carbon, and it is the cis version. Why? Because see, both the groups, this is also a CH3, that's also a CH3, and they are on the same side, hence Z isomer or cis isomer. See, both the hydrogen atoms, which we don't show, they are also on the same side, right? On the same side. That's the Z isomer or the cis isomer. Done? So this version of but2ene will be the cis version, and the trans version is like a chair. We've covered this in a lot of detail in our live classes, right? So it's like a chair if you were to draw the skeletal for it, right? Why is this like a chair? Now you see the CH3, this fella is a CH3 and that fella is a CH3, and this is the hydrogen which we normally don't show in skeletals, and that's the hydrogen. And see, the hydrogens and the CH3s, they are on opposite sides, and that's the trans version for it. I'm just showing you these fellas just so you guys can visualize it, right? If you are bad at skeletals, then that's a problem. You have to work on your basics, because now skeletals are being used widely in the AS level examination, right? So please keep that in mind. Now, moving on. That's one part done. I'm not just solving questions, by the way. I'm reading the questions and talking to you guys simultaneously so that you guys know that the point of solving these questions is to reiterate your concepts. I can go on in solving every single question in very, very, flash speeds, but I'm not going to do that, because the point of doing questions is to make sure that the students revise their concepts through it. Teachers don't need to flex off their skills on how quickly they can do questions. Rather, they should read every single line of the question carefully to teach students their thought process, right? Moving on. So that's one idea. Now it says hydrated rhodium 3 chloride contains 20.5% of by mass of water of crystallization. What is water of crystallization? It's the water molecules bonded in a hydrated salt, right? That's the water of crystallization. Now it says 20.5% by mass of this entire fella belongs to H2O. Now can you guys tell me, hold there, if 20.5% of the mass belongs to H2O, how much of the mass would it belong to RHCl3? How much of the mass would belong to rhodium 3 chloride? If 20.5% of the mass is here for H2O, what is the percentage mass of rhodium chloride? Just subtract it from 100. So 100 minus 20.5, that's what? What do we get? It's just a thought process, 79.5. So now we understood that 79.5% of the mass is for rhodium chloride. Now it says deduce the integer value of X in RHCl3 dot XH2O. So I need to figure out what X is. Now there are multiple ways of solving this question. It's just a simple mole and stoichiometry question, and it's a percentage by mass question. And how do we normally calculate percentage by masses? We say, hey, percentage by mass equals, how do we calculate percentage by mass? It's part over whole divided by multiplied by 100, right? So part over whole multiplied by 100%. That's how you calculate percentages, right? That's how you calculate a percentage of a particular fellow. That's how we kept on doing it in O levels and IGCSE, and even in AS level, percentage yield, right? So that's the idea, not percentage yield, sorry, percentage by mass, percentage composition by mass, right? Now, he is saying that 20.5% by mass is of water. So he's giving me this part of the equation. He's saying, okay, the percentage, I'll give it to you. It's 20.5%, which belongs to H2O. Now I need to tell the examiner, okay, if 20.5% of the mass belongs to H2O, then I just have to plug H2O in this equation. I'll say, okay, my part is H2O's mass, which is what? 18 times X. I don't know what H2O is, right? I don't know how many H2Os I have. This is X, and how do I get 18? Hydrogen is 1, times it by 2 plus 16 here. So 18x is effectively the part mass of H2O that I have, divided by the entire mass of the compound. What's the entire mass of the compound? Can you guys check rhodium in the periodic table? How much is rhodium, guys? Somebody help me out. It's 209.4. Thank you. Chlorine is 35.5 in the periodic table, times it by 3. And then add what to it? Add H2O to it, which is 18, and times it by X, because you don't know how many H2Os do you have. So what is the total mass right here? Somebody help me out. What do you get as the total mass? Achha, it's not 209.5. What is it, guys? Please give me the correct figure. I'm depending on you guys for the figures. I have not done these questions before. It's 102.9. Thank you. So it's 102.9. Sir, I was saying that the sum of these two. Okay, the sum of these two, he's saying, the student's saying, the sum of these two is what? 209.4. 209.4, right? Plus 18x. That's the entire mass of this compound. So it's a simple algebraic equation that has formed. See, you've been given 20.5%, which is equal to what? The part mass of the water, which is 18x, divided by the entire mass of the compound, which is 209.4 plus 18x multiplied by 100%. What happens? The percentage and percentage signs cancel out, and the 100 you can just divide here. So you could effectively just say what? You could say 18x divided by 209.4 plus 18x equals 20.5 divided by 100. And what does this give me? 20.5 divided by 100? 18x divided by 209.4 plus 18x is equal to what? What is 20.5 divided by 100, guys? Somebody help me out. 0.025? Sorry, 0.205. Okay. And can you just plug this in the calculator? You can literally plug this in the calculator. Those who are good in math, they can just multiply on the right hand side, wagera, wagera. But examiner, it's a 2-mark question. I couldn't care less. I'll just plug this in the calculator, and what do I get? What do I get my answer as? What do I get x as? Somebody give me the answer for x. Once you plug this in the calculator, what do you get? You get what? 2.99999, and obviously it's an integer, so 2.999 equals 3. So x is effectively 3. That's one way of doing this question. That's method number 1. Method 1. Now some students say, hey, I don't like method number 1. What if I don't use the part mass of H2O? I don't like this. What if I use the mass of RHCl3? I can absolutely do that. How can I use the part mass of RHCl3? See, for that you must have been given the percentage by mass of RHCl3, and that's indirectly given to you. 20.5 is water, so 79.5% obviously belongs to RHCl3, rhodium chloride. So I can also solve this question from the perspective of rhodium chloride, which is 79.5% by mass is of rhodium chloride. What's the part mass of rhodium chloride? It's what? 209.4, 102.9 plus 35.5 times 3, that's 209.4. So I can just say, hey, part mass is 209.4 divided by the entire mass of this compound, which is 209.4 plus 18x multiplied by 100%. The percentage signs cuts out with the percentage sign. You get 79.5 divided by 100 equals 209.4 divided by 209.4 plus 18x. And once you plug this in the calculator and calculate for x, you're going to get the same answer as 3. You're going to get 3 even now. That's how easy it is. Yeah, I'll open the everyone chat. Please use the everyone chat because it's easier for me to see the everyone chat instead of clicking on everybody's icon. That's method number 2. Now there's also another way, which is the empirical formula way. You can also figure out x through the empirical formula way. What do we mean by the empirical formula way? See, you just take the ratios of the two. You say, hey, 79.5 is the percentage by mass of which fella? 79.5 is the percentage by mass of rhodium chloride, RHCl3. And here you have H2O. What's the percentage by mass of H2O? That's what? That's 20.5. Can you divide them by their ARs? Right? Just like you used to do in empirical formula. Or their molar masses. RHCl3, that's 209.4. And this fella is what? 18. What do you get? The ratio. It's 0. 380. Okay. And what do you get here? 1.14. And now you divide by the smallest ratio. So first divide by AR. That's also a way to do it. And that's actually the better way. That's actually how it's done in the labs. And then divide by the smallest ratio. Just like you used to calculate empirical formula. Right? So what's the smallest ratio? It's 0.380. 0.380. What do you get? 1:3. So X is effectively what? It is 1:3. So rhodium Cl3.3H2O. That's the other method. So these are these three methods of doing this question. The reason why I'm teaching you guys everything is because I am awesome. Sir, how did you cancel percent with percent? See, if this is divide by 100, that's divide by 100. 100 and 100 cuts out. Yes? If you have divide by 100 here and divide by 100 here, this is also percentage and that's also percentage. Right? So keep that in mind. Done, guys? Easy peasy lemon squeezy. You aren't considering 100 in my solution. I am. I'm dividing 100 right here. It's 100%. It's basic O-level math, guys. If you have a problem with percents, don't write percentages. Almas, I've already answered your question. एक साइड पे 100% है, क्या हो गया यार? It's basic math. 79.5% means 79.5 divided by 100. 100% means 100 divided by 100. You can cancel this and this out. क्या हो गया? Percent just means divide by 100, doesn't it? It's 1 over 100. It's 1/100th of something. Come on, yaar. Please don't do this. Don't do this. Done. So I have taught you guys three methods to figure out X. Now I'm saying define stereoisomers. We already know what stereoisomers are. What are they? They are molecules with the same molecular formula but different spatial arrangement of atoms, or different spatial arrangement of atoms, or you could even write it in simpler English. Molecules with the same, molecules or compounds with the same molecular formula but different spatial arrangements of atoms. Of atoms or groups. Or you could have also said they are molecules with the same molecular formula, but they have different what? They have different arrangement of atoms in space. That's also what you could have said. It's okay. Now it says, explain how the conversion of ethene to but2ene can be described as an addition reaction. Remember, a reaction is known as an addition reaction if only a single product is made. That's the identity of an addition reaction. So why is this an addition reaction? The reason why it's an addition reaction is because a single product is made. Right? Or only one product is made. That's also correct. Only one product is made or a single product is made. That's all. That's why it is categorized in as an addition reaction. Now I think draw the two stereoisomers of but2ene. I've already drawn the cis and the trans version of it above. So that's the cis version, and this fella is the trans version for it. Yeah, you need to be good with skeletals. I've discussed skeletals in my live class. See, if those of you who've not taken my classes and are asking these questions that how are you drawing these skeletals, guys, I've spent about 20 lectures teaching you guys introduction to organic chemistry. Not all my lectures are onto YouTube. Won't we make the displayed formula? Nah. Chaudhary, this is not O-level IGCSE. You can make the displayed formula if you want, or you could also make the cis-trans version in the form of skeletals. And I prefer using skeletals, by the way. It's easier and it's quicker. It takes less of your time. Right? So keep on using skeletals. Even if the marking schemes do not show skeletals, you can keep on using them. So how can we get your lectures? You can just contact Miss Naiba for my lectures. Please somebody share Miss Naiba's number in the chat for those who are interested. Next question. Bromoalkanes are used widely in the industry, although there is an increasing concern about their environmental impact. Okay. That's something new to my knowledge. This is how you need to read questions. Enjoy them. I literally enjoy the Cambridge questions because they teach you a lot of things. So now this is something new added to my skill set. I know bromoalkanes are widely used in industries. Now, if you guys are good scientists and after your papers are over, do your research on these questions. That why are bromoalkanes used widely in this industry? Why is there increasing concern about their environmental impact? Learn it. Talk about it, get knowledge, be knowledgeable. This will help you out in the longer run. You'll become a scientist. So it says figure 4.1 shows the reaction scheme involving 1,2-dibromoethane, and he's saying, okay, you have ethene molecule here and you added Br2 to it, and this is what they call reaction 1. What happens? An electrophilic addition reaction takes place, and this is effectively organic synthesis, by the way. These are questions of organic synthesis, which is just effectively knowing your entire organic chemistry and predicting what is going to be formed, right? Just like they are giving you boxes, they'll give you reagents sometimes they'll give you, products, and they'll ask about the reagents. So this is what organic synthesis is all about, right? And I'll also give you guys a quick, long-ass marathon lecture of the entire organic chemistry for organic synthesis as well, right? So this fella is called electrophilic addition reaction, and we already know the entire, electrophilic addition reaction mechanism for it, but I couldn't care less. I just need to know, hey, bromine is added, okay, and what are the conditions for it? It's gonna be added at RTP in a dark room. Effectively there's no condition. It will also take place in a dark room. The reaction will also take place in a dark room, and this is how a 1,2-dibromoethane fella formed. How? The double bond broke, a Br atom bonded here, and the other Br atom bonded here, right? Obviously a carbocation intermediate also formed. And we are not concerned about the mechanism as of now, because he's not asked us the mechanism. Then he's saying, hey, this fella is further reacted with this haloalkane. This is effectively a haloalkane, and haloalkane is reacted with NaOH aqueous here, and here it's reacted with NaOH in ethanol. Now, what's the difference? If you take NaOH in ethanol, or if you take ethanolic NaOH, we know an elimination reaction takes place. And I think by far I'm the only guy who's taught why an elimination reaction takes place if it's dissolved in ethanol, because the OH effectively behaves like a base. The OH behaves like a base. That's why it undergoes an elimination reaction. But if you take OH aqueous, NaOH aqueous, what's going to happen? You're not going to end up with an elimination reaction and form an alkene. Instead, what you're going to do is you're going to undergo a nucleophilic substitution reaction with the OH ion, with the hydroxide ion 90N, with the OH fella. A nucleophilic substitution reaction is going to take place, and after the nucleophilic substitution reaction takes place, we know that the Br atoms are going to be substituted with the OH atoms. So this is one carbon and that's the other carbon, and instead of these two Brs, you're going to end up with what? Two OHs. So tuck, that's the OH here and that's the OH here. That's how it happens. Now, obviously, there is a mechanism for it, SN1, SN2. The examiner has not asked us about the mechanism or anything whatsoever. So we're just going to predict products right here. And obviously, you're going to heat under reflux here. And in this case also, it's good to heat under reflux, because ethanol and even haloalkanes, they are what? They are volatile. So we do not want them to escape. We do not want the reactants to escape. We want a good conversion product. Hence, we heat under reflux. You can even heat, or it's better to heat under reflux, right? And I'll tell you why. See, if I explain one of the reaction mechanism to some of you, for those who've not taken my classes, basically what happens is, if I give you just a haloalkane that looks something like this, it is H, this is H, That's a H, and this is, let's suppose, a Br. I'll use a single Br to make things easy for you, and I'm using the hydroxide ion here. Now what effectively happens is, if the hydroxide ion is ethanolic, it will act as a base. And what does a base do? A base is a proton acceptor. So this fella effectively accepts this proton right here. Now how would it accept the proton? It'll only be a proton if the CH bond were to break. And how does the CH bond break? The 2 electrons shared here go towards this CC bond, and it becomes the pi bond, right? And the double bond forms, right? But we know carbon can make 5 bonds. This carbon has made 4 bonds now, right? The OH accepts this H right here, and this is 1 bond, that's the other bond, and this will become 2 bonds. And this carbon right here, the right hand side carbon, this would have effectively made 2 bonds here, 3, 4, 5. It can make 5 bonds. So one of the bond must go. Which bond is the weakest? The CH bond or the CBr bond? It's the CBr bond which is weaker, and that's how this fella moves out. So what effectively happens is, a Br atom is eliminated and a H atom is eliminated. This OH and H forms H2O, and the Br ion, which is eliminated in the form of bromide ion, it reacts with the sodium ion that you're using. See, you're using sodium hydroxide. So the Br reacts with the sodium ion and forms NaBr, and you end up with an alkene effectively. This is how the elimination reaction takes place. Now obviously this mechanism is not a part of your course, the elimination reaction mechanism, but the reason why I've taught you guys this is for the fact that, you know, the examiner tells you that, hey, you're using ethanol, the double bond forms, and then again you're using NaOH and ethanol, and HBr, H2O and D forms. This is effectively incorrect, by the way. You can read a lot of books on it. The reason why Cambridge examiners say HBr forms instead of NaBr is because they know that the reaction mechanism is not part of your course. But if you are a PSNet Excel student, or if you are an IB student, or any other board, you are following any other board, you should know that HBr formation is incorrect. It's effectively NaBr which forms. Yes, Cambridge is absolutely right when it says that HBr is effectively eliminated. But HBr eliminated does not mean that HBr forms. It's H2O which forms and NaBr which forms, and I've effectively even shown you the mechanism for the elimination reaction. So that's something you should keep in mind for the future even, right? So that's the idea. Now he's saying reaction 3 what happens is you're using NaOH and ethanol and heat under reflux, and so what should happen is this fella should move out, this fella and a hydrogen should move out, this fella and a hydrogen should move out, and you should end up with a double bond because of one of the HBr moving out and another bond because of the other HBr moving out. Effectively you should end up with a triple bond. Why? Because one HBr moves out, the bond goes here, just like from the mechanism I've shown you. See, one OH comes here, takes out the H, double bond forms, and the Br leaves, and the other OH will come to the other Br, the double bond would form, and the other fella would break. So effectively 3 bonds would form right here, and effectively yes, 3 bonds should form. But what the examiner is showing you is he's just showing you a double bond, and he's not elaborated on this particular bromine atom. And what that means is we're just going to stick with what the examiner is telling us. He's saying, what's the name of this fella? What is the name of this fella? It's 1, 2. What is it called? This is 1-bromo-methethene, and we don't write 1. So it's just effectively what? Bromoethene. Now we have to keep this in mind, right? That effectively it should just be carbon-carbon triple bond, that's all. Because this HBr should also leave and this HBr should also end up leaving, right? And I've shown you the mechanism for it even. Now he's saying, hey, before I talk about reaction 4, he's saying now I'm adding an excess of NaOH and ethanol. And so now through these questions and the explanations that the examiner has given me, I've realized that, okay, this is something new to my knowledge. As a student, when I'm solving this, I would have thought like this. But when the examiner showed me this and then he said excess is being added now and something D has formed. So what that means is he's taking out this in 2 steps. And probably this is how it happens in reality as well. In the first step, one of the fella goes, and if you add excess NaOH in ethanol, then probably this Br also goes and the triple bond forms. And this was my thought process all along. So effectively what has formed is just C triple bonded to another C, right? It's C triple bonded to another C, and obviously there's a hydrogen here and a hydrogen here. So what effectively is D? It's basically CH, C2H2. That's what effectively D is. It's 2 carbons and 2 hydrogens. That's all. See, this is how you need to think. It's pretty easy. There's no rocket science behind it. And so what is reaction 4, by the way? Reaction 5 again is also elimination reaction. It's the same idea. And heat under reflux, obviously. And excess ethanol, heat under reflux probably. And polymer C. How should polymer C look like? Now, if you're drawing polymers, you don't need to know the name for it. You don't need to know that it's called ethine or whatever it's called. You don't need to know the name. But If you talk about the polymer, you can either draw the skeletal for it, or you could draw the displayed form for it. I recommend drawing displayed form because it's easier to draw it as a polymer. How do we draw it? See, this is effectively what? Carbon being bonded to two hydrogens, and this carbon is bonded to a single hydrogen and a Br. So effectively this fella looks something like this. It's two hydrogen, then it's a double bond, then it's a carbon, it's bonded to a single hydrogen and a Br. And how would you draw a polymer for it? The double bond breaks and you just extend one line here and one line here, which we call the connectivity bonds. So the double bond breaks and you show one line here and the other line here, tuck and tuck. And you could even cover it in brackets, and you call this N, where N represents the number of monomers or repeat units, right? And what you could have also done is you could have also shown the skeletal for it. How would you show the skeletal for it? Pretty easy. See, you have two carbons and you have to show the connectivity bonds even. So what I do is I'm going to show the connectivity bond right here. This is my first connectivity bond. Then I'm going to draw two carbons. See, this is one carbon, that's the other carbon. This fella is the connectivity bond. When you extend the line and make it go out of this square bracket, that represents connectivity bond. This does not represent a carbon. Please, it does not represent a carbon. This literally represents a connectivity bond. This is a carbon, this is this carbon, and this fella is this carbon right here. And we know that the right carbon has a Br atom also bonded to it. So I can even show the Br atom right here. And then I'm going to show another connectivity bond. And that's all. See, connectivity bond here, connectivity bond here. This is connectivity bond. Then one carbon, two carbon, one carbon, two carbon. Br bonded, Br bonded. Connectivity bond, connectivity bond. That's how you would have drawn, the skeletal for it even. Won't we add space between carbon and connectivity bond? No, in skeletal, this is how you draw it. You just make sure that you add square brackets. There's also one more way of drawing these polymers, which some books represent, and even you'll see it sometimes in Cambridge marking schemes, which is you show the connectivity bonds with dots as well. So that's also possible. If you show it with dots, that's also possible. So in reaction 2, would NABR not form? No, why would in reaction 2 we are only concerned about the nucleophilic substitution reaction taking place. Right, H2O forms, and yeah, that forms. Yes, it does, but we're not concerned about it. I just wanted to clear out this confusion right here in elimination. You could do the mechanism for it to figure out what forms. Absolutely, Rama, you're right. Sir, is a diol formed in reaction 2 because the two Brs are substituted? Yes, if two Brs are substituted, then obviously if you have two OHs, then obviously a diol is formed. Sir, Cambridge asks about the explanation of heat under reflux. I've already explained it. Heat under reflux literally means that you heat it, but you also use a condenser to make sure that the volatile reactants don't escape and they fall back into the flask, right? And so that you can get a good conversion product. I will explain heat under reflux in a lot of detail, and let's just not deviate from the things, right, from this particular class. Complete figure 4.2 to show the mechanism for the formation of 1,2-dibromoethane in reaction 1. Okay, as it include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. We've done this a billion times. We know that this fella is going to be partial positive, this fella will be partial negative, and that's why we call it electrophilic addition reaction, because it's the electrophile which initiates the reaction. This is partial positive, and this pi electrons are going to attack this fella right here. So the moment these pi electrons attack this electrophile, we know that the Br-Br bond will now break heterolytically and not homolytically, and both the electrons will go to this Br atom right here. And make sure, try your level best to, show the curly arrows from the middle of the bond. That's just a convention. You can show it from the middle of the bond, right? And please show the dipoles. This is not partial negative. A partial negative will never be attacked by pi electrons. It's the partial positive which is attacked by the pi electrons, right? No, Chaudhary, that's not the correct way. It's not the correct way of drawing that polymer. No, you don't show spaces. Whoever have taught you to show spaces, that's incorrect. Sorry to say. Now, what's going to happen? what's going to happen is a carbocation intermediate is going to form. Now, which carbocation intermediate is going to be formed? It's a symmetrical alkene, so it doesn't matter. You can make this fella into the carbocation or this fella into the carbocation. It's a symmetrical alkene. If it were asymmetrical, then we would use the Markovnikov's rule, or we would use the more substituted carbon rule, or the more stable carbocation rule. So in this case, it doesn't really matter. One of the Br will be attached to the carbon right here, and then this fella will be the carbocation intermediate attacked by this particular nucleophile when it has a lone pair right here. So let's show it to the examiner. Let's show it. So these are the two carbons. Now these two carbons, one of these two carbons will now have the Br bonded to it, and this fella will be the carbocation intermediate, and you have a bromide ion right here, and the bromide ion is going to attack this carbocation intermediate like so right here. Done. And this is how once this fella attacks this guy, you're going to have with one, you're going to end up with 1,2-dibromoethane. And this is how literally I get 3 marks for nothing. I'm getting 3 marks for nothing. Literally nothing. Just make sure to show the curly arrows. Remember, curly arrows represent the movement of electrons. You can't draw an arrow from the positive charge to here. No, that's incorrect. The electrons movement are shown by the curly arrows. So it's the electrons which move towards the carbocation intermediate. It's not the positive ion which moves. There's nothing in here which is supposed to move here, right? So that's the idea. So why does it have 2 electrons? Both the electrons from the lone pair went towards the pair. Yes, it has other lone pairs as well. That's true. But we just show the 2 electrons that went from this bond right here. That's all. Done? Any questions up until now? No questions? Let's keep on moving forward and keep on scoring marks. The enthalpy change of the reaction 1, which is given right here, this reaction 1 enthalpy change, is saying this is minus 90 kilojoule per mole. Okay, it's minus 90 kilojoule per mole. Okay, now I think the enthalpy change of formation of ethene is plus 52.2 kilojoule per mole. Now, what is enthalpy change of formation? If you've forgotten these things, I can't help you out. You need to remember them. Enthalpy change of formation, you need to know the definition to be able to solve these questions. And what was the enthalpy change of formation? It was when 1 mole of a substance formed from its elements in its standard state under standard conditions, right? And the standard enthalpy change of formation, right? So what effectively we mean by this is, if I were to talk about the enthalpy change of formation of ethene, I would take the elements right here. We don't even have to write the equation for it. I just take the elements, the carbon, which is effectively graphite and hydrogen right here, and I'd say carbon and graphite and hydrogen, carbon, which is effectively in the form of graphite, that's the standard state of carbon, and hydrogen, they're going to combine together to give you ethene. And what's the reaction for that? What's the enthalpy change of formation for that? It's plus 52.2 kilojoule per mole. I'm just going to add this here, plus 52.2, right? And what it asks me in the calculation is, it's saying calculate the enthalpy change of formation for 1,2-dibromoethane. So I need to figure this fella out, and I know Hess cycle, the indirect root equals the direct root. So plus 52.2 plus minus 90. Please remember, don't write minus 90. It's the law of summation, right? Remember, it's the law of summation that Hess cycle follows. So it's not, you can't write 52.2 minus 90 directly. It's going to be considered incorrect according to me. But according to the examiner, maybe he gives you the mark for it, maybe he doesn't. But according to me as a scientist, I know it's the law of summation. So you sum things up. Yes, it's minus 90. That's why I'm writing it in the bracket. See, the indirect summation equals to the direct summation. So plus 52.2 plus brackets with minus 90 would be equal to x. And now you can open the bracket. So plus 52.2 minus 90 equals x. What is x equal to? Somebody help me out. Minus 37.8. Thanks. Kilojoule per mole. Minus 37.8. Done. I think complete figure 4.1 to draw the structure of compound A. We've already drawn it right here. See? It's already drawn. It's a diol. Ethane 1,2-diol effectively. Now I think name compound B. Where is compound B? Oh, we've already named compound B. See? It's bromoethene. Next. See, that's how easy these things are. He's saying draw the structure of one of the repeat unit in polymer C. We've already drawn it. I'll draw it again here. Yeah, it's H. That's H. That's H, that's the Br fella, and these are your connectivity bonds. He just wanted one repeat unit, so there's no need to write bracket, no need to show square brackets and N, because that would have been the entire polymer, just one repeat unit. That's what he's asking. I think in reaction 5, compound B reacts with an excess of NaOH dissolved in ethanol. The products are HBr, H2O, and an unsaturated hydrocarbon. This is even helping you out, unsaturated. Suggest the identity of D. Again, we've already done that at C2H2. And remember, this is not HBr. Effectively, it's NABR. But Cambridge knows that since it's not part of your course to know these things, he's teaching you even the incorrect idea. Yeah. Now, any questions in this particular part? We're going to solve the other question right now, the 2024 question number 3. How many questions are there for the 2024 set? They can keep one thing in mind. Me solving even 3-4 questions with you guys is worth somebody else solving 20 questions, because what matters is the quality with which you solve questions. This is what would, help you out effectively in your exams, and when you are solving questions on your own, these slow explanations, everything being considered. If I just want to go blah 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 blue blah blue blah blue blue blah 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 blue blah blah blah, you would have just those would have students who would have already done everything would have gotten stuff, but those who are just for the first time sitting in the class would have been just blank. We just have 5 questions in the 2024 set. That's actually good then. Anybody? Any questions? Any questions whatsoever? Shabash, jaldi. Any questions? No questions? Move forward. Okay, moving forward. Question 3. In electrophilic reactions involving alkenes, the pi bond of the C double bonded to C is broken. Obviously, why would the pi bond be broken? Because it's weaker. Why is it weaker? Because what happens? The shared pair of electrons lay above and below the internuclear axis. There's a greater distance between the nuclei and the shared pair of electrons, since they lie above and below the plane, above and below the internuclear axis, right? Now, he's saying suggest one difference between the sigma bond, and the sigma bond is stronger. It does not break. He's saying just tell me why sigma bond does not break, or why pi bond breaks. I'll explain why the sigma bond does not break. Why would the sigma bond not break? Because the sigma bond is stronger. Sigma bond is stronger. And why is the sigma bond stronger? Because the shared pair of electrons, lie closer to both the nuclei. Right? And that's the reason why there's stronger attraction. Thus, stronger attraction. And that's why it does not break. The shared pair of electrons, there's a head-on overlap. Absolutely, you're right. There's a direct overlap, a head-on overlap. In pi electrons, there's a sideways overlap. There's a lateral overlap. There's an axial overlap. You can use any word for it. Right? So you have to talk about the attractions. Hence, stronger attraction in the sigma bond and does not break, compared to the pi bond where there is weaker attraction, as the shared pair of electrons lay farther away from the nucleus or the nuclei, as the shared pair of electrons are above and below the internuclear axis. And in this particular case, they are on the internuclear axis. Right? I think complete figure 5.1 to show the mechanism for the electrophilic addition of hydrogen bromide to blah blah blah. It's pretty simple. Show the dipoles. This is partial positive, and these are permanent dipoles, by the way. This fella is more electronegative. The shared pair of electrons lay closer towards the Br atom, and thus this fella is partial negative. Now, how would you show the electrons? Again, I'm going to show the electrons attacking the pi electrons, attacking this electrophile right here. And so when it attacks, I'm going to try to ensure that it's from the middle of the bond. And I know that we already know that the electrons lay closer towards the Br, but it's good in a conventional manner to show the electrons from the middle of the bond, right? So this fella attacks this guy, and we know hydrogen can only make a single bond. It can't make 2 bonds. So what happens is this bond breaks heterolytically, and both the electrons move towards the Br, right? And this is what happens. You have C bonded to H, bonded to H, and then you have CH3 right here, and that's CH3 right here. Now the question is, which fella should be the carbocation intermediate? There are multiple ways of knowing these things. Now one shortcut that your teachers teach you, and that's effectively, I don't like using this shortcut because it's good to know the stability of carbocation intermediate and why that happens and how that happens, because the examiner always asks you about the explanation. But in case the examiner does not ask the explanation, the question is, because it's an asymmetric alkene, where should the hydrogen go? Markovnikov's rule, how are you spelling Markovnikov? It's absolutely incorrect. I must please learn the spelling. This is not the spelling for it. But Markovnikov's rule basically states that the hydrogen should bond to the carbon which is already bonded to more hydrogen. So this fella should go here, right? And therefore this fella should be the carbocation intermediate. This will be the major product, right? And whenever the examiner is not asking you about the major product, the minor product, show the major product. But he's also stated it in the question that please, it produces the major organic product. What that means is that this fella should be the carbocation intermediate. But I like the proper explanation to it, which is the fact that whenever the pi electrons attack this fella, the hydrogen would go, the positive charge would form on the more substituted carbon. The more substituted carbon means the carbon which is bonded to more carbons. That's the more substituted carbon. Or that's also a shortcut. Then the third explanation to it is the actual explanation, which is the fact that the carbocation that is going to form should be the carbocation which is more stable. This fella is bonded to 3 alkyl groups, which means that it's a tertiary carbocation intermediate. If this fella were to have the positive charge and the hydrogen were to go here, then this fella, since it's only bonded to 1 alkyl group, this would be the primary haloalkane. So between tertiary and primary, which one is more stable? It's the tertiary haloalkane which is more stable. Sorry, it's the tertiary carbocation intermediate which is more stable, not haloalkane, what am I saying, which is more stable. And that's why this ends up forming. Why is it more stable? Because the more alkyl groups you have, the greater the alkyl inductive effect, because we know that alkyl groups, they donate electrons through the sigma bonds. They have the electron donating tendency, which we call the positive inductive effect, and that stabilizes this positive charge, therefore making it more stable. It spreads out this positive charge, makes it more stable, and thus the tertiary carbocation intermediate is more stable than the primary carbocation intermediate, or for that matter even the secondary carbocation intermediate. So this is something we should know. The explanation is in fact part of our course. But whenever the explanation is not asked, you can use the Markovnikov's rule, or you could say the positive charge should form, or the carbocation should form with the more substituted carbon, which is effectively the carbon bonded to more carbons. This carbon is bonded to 1 carbon, this carbon is bonded to 3 carbons, so this should have the charge. This is how you can actually use these tricks. But the problem is with a lot of students, because they just learn Markovnikov's rule, they forget about the positive alkyl inductive effect. So please don't forget about that. And then obviously you have the bromide ion here, and this fella, sorry for my curly arrow, this fella attacks this guy, and you end up forming CHH. And what happens? This was the H here, this is CH3, and this fella is your PR. That's the major product. Sir, can we say carbocations are mostly at the tertiary? No. You can say it for your brain, but you can't say it in this to the examiner. If you say this to the examiner, he'll give you 0. Electricity, it's all about being more scientific. A levels may, and even in O levels, what a lot of, for logic's sake you can state, but please don't remember logic. If you were to just remember, like, rote learn something, you could rote learn Markovnikov's rule or the more substituted carbon rule. But please just rote learn, don't rote learn these, just understand the idea behind it. Yeah, done. Always talk about the alkyl inductive effect, the positive alkyl inductive effect. Next question. Now, M reacts to form R by the addition of one reagent as shown in figure 5.1. Okay, and if you check this fella out, see, you had an alkene here and now you have a diol. Which reagent have you used? This is what effectively organic synthesis is. Don't put question marks. It is diol, absolutely, but what reagent did you use? How do we take an alkene and oxidize it to a diol? Obviously we use what? Cold dilute potassium manganate, right? That's what we use, and the double bond breaks, you get a diol right here, tuck and tuck. Now I think identify the reagent and the conditions for this reaction. It's cold dilute KMNO4. Now, here's a question from my end. The problem is that the examiner tends to switch up their answers, and please do not follow marking schemes. I would recommend not just writing cold dilute KMNO4, I'd also recommend writing cold dilute KMNO4 and writing acidified here or alkaline even. You need to either write acidified or alkaline, or represented with represented like this, KMNO4 slash H plus. Now the problem is in the 2-3 variant, let me tell you something. In the 2-3 variant, it's more logical, the 2-3 variant. And the 2-3 variant talks more about logics even though it has not been taught to the students, which is the fact that sometimes if you have acidified aqueous, if it's acidified, cold dilute KMNO4, if sometimes it's acidified or it's alkaline, what would end up happening is this acid can actually even rupture the bond. That's the problem. And that's why even if you check the marking scheme out for the June 23 papers, I don't know if this marking scheme would say it like this, but it would have not mentioned the concept of acidified. But as you go down in the papers and you go on to your own variants, which is the 2-2 variant or the 2-1 variant, they would have written acidified or alkaline conditions. You can use acidified or alkaline conditions, it doesn't really make a difference. We normally use acidified. You've not been taught alkaline, so I'll just erase it. All right, slash H plus. Happy? Now happy. So you need to write acidified as part of the chemical. Acidified just represents that you are adding hydrogen ions, and it's normally in the form of H2SO4. So if you're a student who's going to appear in the 2-2 exam or the 2-1 exam, you'll mostly notice that whenever you talk about diols forming, you will write cold dilute acidified KMNO4 or cold dilute KMNO4 slash H plus, right? Which we've normally learned even in the classes. But if you're a 2-3 variant student, sometimes the examiner says, hey, if you have a lot of hydrogen ions, it can even contribute to breaking the entire carbon-carbon double bond, to rupturing the bond and forming what? Using the oxidative cleavage idea, it can form different products depending on what's being bonded. So that's the idea, and you need to check with your variants if you're a 2-1 student, 2-2 student, 2-3 student. And this type of clarity will never be shown in any books or in any examiner. Teachers, what they do is they just write whatever is written in the marking schemes. That's all. What response would be the best right here? I already wrote and I told you the conditions. You're not a 2-3 student, are you? You're not a 2-3 student, right? Cold dilute acidified KMNO4, the way I've written it, right? But if you're a 2-3 student, then you'll even see that in their marking schemes, the acidified ion is not written, and I've even given you the explanation for it. Khair. R is also made from M by 2 steps, as shown in figure 5.2. Now it's made from M in 2 steps. And which 2 steps? See, alkene first went into a haloalkene. How? He used Br2. The carbon-carbon double bond broke. One Br, each of the Br went to each of the carbon in the double bond. And then, how did this happen? This happened at RTP in a dark room. In a dark room. Done? And then the Br fell, the haloalkane went into an alcohol. How did haloalkenes go into alcohols? It's the nucleophilic substitution reaction, KOH or NOH, but it shouldn't be ethanolic, because then if it were ethanolic, then double bonds would form. But it's not ethanolic. It should be aqueous for the OH minus ion to act as a nucleophile rather than a base. And obviously heat under reflux. Heat or heat under reflux. I'll use HUR. Because haloalkenes are normally, they are volatile. So you can write heat or heat under reflux, doesn't really matter. Better thing to write is heat under reflux. Right? So identify the reagents and conditions for step 1 and step 2. Reagent is Br2 at RTP in a dark room. And number 2 is what? NaOH aqueous. And what do we do? We heat under reflux, or just heat. Couldn't care less. Yeah. Done. Name the mechanism for step 1. It's electrophilic addition. Last question of the 2024 set. Chlorine reacts readily with propene to form K, 1,2-dichloropropane. Okay. And it's obviously an electrophilic addition reaction at RTP in a dark room. It's going to take place. K can be used to form L. Okay, that's something interesting. K is a haloalkene. And L may, if you check this out, the difference between K and L is that K may, you had two halogen atoms, but in L, you have an alkene bond. Now, how do you go from haloalkenes to an alkene? How do you go from haloalkenes to an alkene? This is not an alkene, Chaudhry Ali. It's not an alkene, it's an alkene. For an alkene, then you need a UV light and a free radical substitution takes place. And again, the spelling of radical is incorrect. Raima, please don't mess up the spellings in the mechanism. Like if I were to write the spelling of electrophile as, like this, it'll cause a problem, wouldn't it? If I write electrophile as pedophile, it'll be wrong. It'll be incorrect. Epstein file. Yes, spellings, such spellings cost marks. Start rote learning spellings for crying out loud. मतलब radical की spelling अगर आप गलत लिख रहे हैं तो there's a problem. There's a problem, right? Right? Please. Don't take the Cambridge examiner so lightly. The exam is easy if you start following instructions. Students who don't follow instructions and say, can we write this? Can we write that? Can we write like this? Can we write the answer like that? Go on, by all means. Do whatever you want to do. If it costs you, you're right. You can even hang yourself off the ceiling for all that matters. It's okay. You can do it. Everybody is entitled to whatever they want to write. My job is to teach you the structured course of the Cambridge exam. Okay, so we see that an alkene or effectively a carbon-carbon double bond forms. So how do you go from haloalkane to effectively an alkene? How? It's NaOH, but not aqueous. It's ethanolic and heat under reflux, right? This is complete figure 2.2 to show the mechanism of chlorine with propene in reaction 1. So pretty easy. This would be the electrophile. That's partial positive, partial negative. The pi electrons attack this fella. This bond breaks heterolytically. You end up with a carbocation intermediate. And see which carbocation intermediate should form. Should this have the positive charge? Should this have the positive charge? Obviously, this would give you the more stable carbocation intermediate, which will be the secondary carbocation intermediate. And this fella will give you the primary carbocation intermediate. So this fella is the major product, right? See, he's not mentioned anything about the major product. So I'll assume that he's talking about the major product, right? So this is hydrogen. This is CH3. And this is the positive carbocation intermediate, and even the Markovnikov rule that the hydrogen bonds to the carbon with more hydrogens, right? And then this, hydrogen chlorine bonds here, right here. So the first, see, if you're using Markovnikov's rule here, it fails because there's no hydrogen involved. Then you say Markovnikov rule says that the electrophile, the first fella, should bond to the carbon with more hydrogen. See, here the Markovnikov's rule doesn't make sense here, because there's no hydrogen involved here, is it? It's just ClCl. Hence, you need to know the more substituted carbon rule, or you need to know the concept. Sure, you can do that. Sure, Raima, you can do that. But then you will also tell the examiner, see, don't try to be cheeky with the examiner. Raima is saying, sir, instead of, adding NaOH aqueous here, what if I add AgNO3 aqueous here? I've taught you this, absolutely. But is the examiner telling you that there's a precipitate here? Is the examiner telling you that there's going to be a precipitate form? Is the examiner telling you this stuff? Don't try to make things complicated for yourself. If the examiner is not, if you write this, 0 marks. Congratulations. Please don't try to be cheeky with the examiner. Please. I'm not trying to scare you. I'm just saying, follow my lead. And so the lone pair is now going to attack this guy. And this is how the fella forms. Identify the reagents and conditions for reaction 2. Reaction 2 again, NaOH or KOH, ethanolic, heat under reflux. So NaOH, because elimination reaction takes place, ethanolic, or dissolved in ethanol. And heat under reflux, or write heat or heat under reflux. Because again, haloalkenes are effectively what? They are volatile. So you have to be careful with them. Draw one repeat unit of the addition polymer that forms from L. Now where's L? L is this fella right here. Now again, it's up to you whether you want to show the skeletal for it or whether you want to show the displayed form. In polymerization, I'd prefer just showing this the displayed formula, because a lot of students, they find it easy since you've been doing this since the exams, since the start of time. This is one carbon, that's the other carbon. This is a chlorine atom, and this fella is effectively a CH3. So if I were to show it to the examiner, this is a Cl, this fella is a CH3. That's the carbon-carbon double bond which is going to break. This is going to be a carbon. See, this fella is bonded to two hydrogens, which we don't show. Two hydrogens, and that's the repeat unit right here. These are the connectivity bonds, or you can show it with dots. And we are done with the 2024 set for alkenes. Any questions? See, after this we start off with a 2023 set. I am tired. Any questions whatsoever, ask away. Hanji. I've had a rough day, sorry. Sorry for taking it out on you guys. I'm sorry. Just had a rough day at corporate. Yeah, some fights. Sir, electrophilic substitution वाला एक दफ़ा समझाइएगा जिसमें वो, it's not called electrophilic substitution, it's called an elimination reaction. Chaudhary Saab, watch the recording please. Sorry, I can't explain, it's not part of your course, so I'm not going to explain it. And yeah. Sir, how many sets would we be doing? Sorry to annoy. No, Rubab, you're not annoying me at all. That's okay. We'll be doing sets from time to time. Whenever I get time, I do questions with my AS level class, and when I do it with them, I also send you guys the link, because my AS level students, there are 106-7 students in my live class, but pathetic how only 6-7 show up to the live class. Everybody else just watches the recording. Hence, I shared the link with everybody across the globe, because I want as many students to just join in for the class to be as interactive as possible. Those who think, we're just messing around here, by all means, don't join. But somebody's gonna get cooked in the exams. A levels is easy, but there are a lot of inexperienced teachers out there, and those teachers, they don't understand the magnitude and the importance of scientific knowledge and keywords and key terms. A lot of fraudias in the market even, who teach incorrect concepts. I'm sorry, I'm not that guy. So, any questions, or should we call it a day?